Welcome to this explainer. Today, we're taking a deep dive into the wildly fast-moving world of AI engineering. I mean, think about it. If you look back just a few years, artificial intelligence felt like this highly specialized, top-secret research lab project. You needed massive teams of PhDs, insanely specialized infrastructure, and honestly, years of runway just to get off the ground. But today, wow, that barrier to entry is completely collapsed. The rise of foundation models, served right up as APIs, has totally transformed AI into a standard, super powerful development tool. It's accessible to almost everyone now. You can literally build applications without writing a single line of code. But, and this is a big but, with all that new accessibility comes a completely new set of engineering rules for business leaders and developers alike. Let's get into it. Here's our blueprint for today's explainer. We're going to hit 5 key areas. First, the AI engineering shift. Second, bridging product and engineering. Third, the last mile challenge. Fourth, systematic evaluation, and finally, designing for scale.
All right, starting with section 1, the AI engineering shift.
So when we look at how we actually build with AI today versus traditional machine learning, I really want you to ask yourself, is your organization treating AI as a high-risk science experiment or as a standard development tool? Because thanks to the model-as-a-service approach, the ones popularized by companies like OpenAI and Anthropic, models are now exposed via simple APIs. You don't necessarily have to drop a massive upfront investment to train a proprietary model entirely from scratch. Instead, you're adapting models that someone else has already spent millions of dollars to train. And listen, this isn't just a minor update in your tooling stack. It is an entirely new discipline.
We are looking at a massive paradigm shift here. In traditional machine learning engineering, you started with your data, you used that to train a model, and then, finally, you built a product around it. But modern AI engineering, it flips that completely upside down. Now, you start with the product idea, because hey, the model already exists. Then you use data to adapt that model, whether that's through context retrieval or fine-tuning, to fit your specific use case. And since so many teams have access to the exact same foundation models, your competitive edge absolutely has to happen in that application development layer. That's where the magic is now.
And you better believe the market is paying close attention to who's adopting this new paradigm. Look at the financial data. S&P 500 companies that even just mentioned AI in their earnings calls saw an average stock price increase of 4.6%. Compare that to just 2.4% for the companies that didn't. Now, whether that's direct causation or maybe just a correlation showing that agile companies naturally do better, the takeaway for business leaders is crystal clear. Understanding and integrating this transformational tech, it's no longer optional if you want to stay competitive.
Moving right along to section 2, bridging product and engineering. Because AI isn't just some invisible back-end optimization anymore, it literally defines the user experience now. You have to make some serious strategic decisions about its role in your product. If you're a leader trying to set up cross-functional collaboration, you've got to ask, is the AI absolutely critical? Think about Apple's Face ID. The feature wouldn't exist without it. Or is it complementary, like Gmail's Smart Compose, where the core app works just fine if the AI breaks? Also, does the AI just react to a user's prompt, or does it proactively jump in with suggestions? And perhaps most importantly, what's the role of the human in all this? Is the AI just running background support, or is it making the final call? Nailing down these answers dictates everything: your engineering requirements, your risk tolerance, and just how bulletproof that system ultimately needs to be.
Which brings us to section 3, the last mile challenge. Okay. Navigating the transition from a flashy internal concept to a real, robust, user-facing system introduces a huge danger. I call it the demo trap. It perfectly captures this idea. Because the base capabilities of foundation models are just so incredibly impressive right out of the box, an engineer or a product manager can slap together a mind-blowing demo over a single weekend. But wow, that initial success is incredibly misleading for business timelines. Bringing that weekend demo to actual production reliability, handling all those weird edge cases, ensuring consistent latency, mitigating hallucinations, that takes months of grueling, systematic engineering. Seriously, do not let a weekend demo trick your product teams into thinking the hard work is already done. So how do we fix that? Section 4, systematic evaluation.
To survive that deceptive last mile, we have to focus on what is arguably the single hardest challenge in AI engineering today. Historically, the AI community poured massive amounts of money into developing complex algorithms and training larger models, while systematic evaluation tools, they got almost zero attention. But recently, as the industry finally wakes up to the challenge, we're seeing this massive, sudden spike in open-source evaluation repositories. And thank goodness, because evaluating open-ended foundation models is way harder than traditional machine learning. Back then, a simple spam or not spam label usually did the trick. Today, a lot of teams literally just eyeball the results to see if they look right, which is a massive liability. We absolutely need structured, automated evaluation infrastructure.
The absolute gold standard we're striving for here is functional correctness. This is the ultimate metric for any application. Think about it. If you ask an AI to write code, does that code actually run without throwing errors? If you ask it to book a restaurant, does the reservation actually go through? For business leaders, this is what actually matters. Not how flowery the text is, but the utility of the action. But measuring functional correctness for these open-ended, probabilistic AI outputs, it is a huge engineering challenge. It requires sophisticated pipelines, and get this, sometimes you even have to use other AI models as judges just to evaluate the outputs.
Now, before you start throwing your precious compute budget at a perceived quality problem, you really need to understand the difference between these two levers. Prompt engineering involves experimenting with the instructions, the retrieved context, and the sampling variables of an existing model. It's fast, it's highly iterative, and most importantly, it's cheap. Fine-tuning, on the other hand, actually goes in and updates the internal weights of the model itself. That requires carefully curated data and significant compute power. The core lesson for your team? You must implement systematic experimentation and test for quality via prompt engineering and context retrieval first. Do not jump straight to costly fine-tuning unless you have completely exhausted the capabilities of your baseline model.
Okay, moving to our final area, Section 5, Designing for Scale. When you're out there designing scalable AI systems, you are constantly battling constraints. I mean, compute is rarely infinite, right? The scale of a model is generally signaled by three main proxies: the number of parameters, which dictates its actual learning capacity, the number of training tokens, which shows how much data it actually learned from, and the number of flops, which translates directly to your training cost. Unless you're sitting on an unlimited budget, you have to design compute-optimal models. There's this well-known heuristic called the chinchilla scaling law, and it's a real game changer. It helps engineering teams calculate the absolute best model performance they can possibly achieve for a fixed, predetermined budget.
Now, if you thought just throwing more compute at the inference stage was some magical solution, data from OpenAI actually suggests otherwise. They found that, yeah, asking a model to generate multiple different outputs for a problem and then picking the best one does improve performance, but only up to a point. At exactly 400 completions, the solve rate actually peaks, and then it literally starts to decline. No way, right? Not only does sampling thousands of outputs become astronomically expensive, but it actually increases the chance of generating an adversarial output that tricks your own verifier. The takeaway? More scale isn't always better, smarter scale is.
Which brings us to our final thought. As we've seen today, the shift from machine learning research to product-driven AI engineering basically changes everything. It changes how we collaborate across teams, how we evaluate functional correctness, and how we manage those tight compute budgets. So, I want you to look closely at your own organizational charts, your development pipelines, and your product roadmaps. Are you truly set up to engineer scalable, robust software with foundation models today, or are you still operating a very expensive, slow-moving science experiment? It is absolutely a critical question to answer. Thank you so much for joining me on this explainer.